Hey everyone, welcome to ILS Concepts for Electronics Technicians. This is Lesson 3, Localizer RF Pattern Development. In this lesson, we're going to begin with a discussion on vector line analysis, which is going to be necessary in describing how localizer RF patterns are developed. All right, let's start with the polar coordinate diagram. Now, a vector represents two things: amplitude, shown by the length of the arrow, and phase, shown by the direction of the arrow. It can be seen here that when we delay a signal, it moves in a clockwise direction. And when we advance a signal, it moves in a counterclockwise direction. And this concept is going to be important to remember as we're going to revisit it again and again through vector analysis. All right, so to reiterate, the length of the vector indicates the amplitude of the signal. Here you can see vector A and B are equal in amplitude. And now A and B are unequal, with the amplitude of vector A being larger than vector B. Here you can see this vector represents a signal that is at 0 degrees. By comparing the two vectors, you can see signal A and signal B are in phase. Comparing these two vectors, we can see that they are 180 degrees out of phase. And in this example, vector B has now been delayed 90 degrees relative to vector A. When adding vectors, the beginning of the vector is the tail and the end of the arrow is the tip. So to add two vectors, we simply place the tail of vector B at the tip of vector A. The resultant vector is from the tail of A to the tip of B. In this example, two vectors, 180 degrees out of phase and at different amplitudes, are added. Once again, we place the tail of vector B at the tip of vector A, and the smaller vector is the resultant. In this example, vectors A and B are equal amplitude, but B has been delayed 90 degrees out of phase with vector A and yields the resultant shown by placing the tail of vector B at the tip of vector A and drawing a new line between the tail of A to the tip of B. In trigonometry, we could obtain values using the previous example. Let's just read the word problem here. Vector A has an amplitude of 1 and a direction of 0 degrees. Vector B has an amplitude of 1 and direction of negative 90 degrees. Find the amplitude and direction of VA plus VB. So vectors have an x and y component. So in vector A, the x component is the amplitude of the vector 1 times the cosine of the angle, which is 0 degrees. The y component is vector 1 times the sine of the angle, which is 0 degrees. In vector B, the component is the amplitude of the vector 1 times the cosine of the angle, which is negative 90 degrees. And the y component is the vector 1 times the sine of the angle, which is negative 90 degrees. The result is a vector sum whose coordinates terminate on a graph of x equals or at x equals 1 and y equals negative 1. However, we still need to find the amplitude and direction of the vector. So we can use Pythagorean's theorem to find that the amplitude is a 1.41. Using the arctangent of x over y, we find the direction at negative 45 degrees. Now, a vector line is used to describe two things: amplitude and phase, and we can use them to describe how RF patterns develop, the relationships of the 90 Hz and the 150 Hz signals, and how CSB and SBO signals combined. So let's begin with how the localizer RF pattern is developed. So let's begin this discussion on the localizer log periodic dipole antenna, or LPDA, which consists of 7 horizontally polarized half-wave dipole elements. The elements are spaced at intervals following a logarithmic function of the frequency. The length of the elements and the spacing between gradually decrease toward the front of the boom. Not all dipole elements, though, are active at any given frequency, and only the active regions will contribute to the radiation. And lastly, each antenna is mounted on 7-foot-tall frangible supports designed to easily break away in the event of an aircraft strike. Okay, so here we have a log periodic dipole antenna array, which is a 14-element array type. Some localizer antenna arrays could be only 8 or up to 20 antennas. This is referred to as the aperture of the array. And from the shelter, RF cables feed these systems, which consist of the CSB and SBO signals, which are buried underground, to the antenna distribution unit. Through the distribution unit, the CSB and SBO signals are distributed to the various antenna pairs at the proper phase and amplitude to form the localizer radiation pattern. Let's now look at how the antenna array spacing between pairs, known as A spacing, affects the radiation pattern. In this first example, we'll consider each pair at a time whose signals are in phase as they leave the antennas. In summary, the wider the antenna array spacing, the narrower the pattern. And conversely, the narrower the antenna array, the wider the RF pattern. The number of antennas used in a localizer antenna array is largely dependent on environmental and siting factors where nearby objects could interfere. So generally, smaller 8-element arrays are for flat wide open airfields, while the larger 20-element arrays are for congested airfields with many nearby buildings and hangars that could be sources of reflection. Let's now look at the RF pattern of antenna spacings where the signals are out of phase as they leave the antennas. Okay, we're finally ready to analyze the development of the localizer RF pattern in greater detail using vector line analysis. And for simplicity, we will consider just one pair of antennas from a localizer antenna array. And this example does not include modulation, only the RF pattern developed. This pattern results with or without modulation. Later lessons will consider the effects of modulation, but for now, just focus on the pattern development. The distribution unit and the antenna feed cables have already set up the CSB signals to leave each antenna in phase. Since the path lengths of the signals from each antenna are the same, they're in phase and add together to create a greater signal strength amplitude on centerline. This is also known as constructive interference. In this direction, we see that the CSB signals still leave each antenna in phase. However, as we move away from that center line, the path lengths of the signals from each antenna is different, and they are now slightly out of phase and don't completely add together, creating a weaker signal amplitude away from centerline. This is also known as deconstructive interference. At some point away from centerline, the path length from the right antenna is 180 degrees longer than the path length of the left antenna, and they are totally out of phase, resulting in no signal strength and nearly complete deconstructive interference. And now let's move back to centerline, where the same process occurs to the left of centerline. On the same pair of antennas, the SBO RF pattern is set up by the distribution unit and the antenna feed cables to leave each antenna out of phase between the pair and 90 degrees out of phase with the CSB. Later we will see why the SBO is in quadrature to the CSB, but for now, just focus on the fact that the SBO signals are 180 degrees out of phase between the left and right antennas, with the left antenna being delayed 90 degrees and the right antenna advanced by 90 degrees. Since the path lengths are equal, but the signals are oppositely phased along the center line, a deep null occurs. This RF pattern is a major part of how coarse alignment is achieved. So as we move away from the center line, the SBO signals still are leaving each antenna out of phase. However, the path length differences are now causing the signals to become in phase and adding together, thus creating a stronger signal strength amplitude from centerline. Now at a further distance still from centerline, the SBO signals are still leaving the antennas out of phase, but the path length differences are such that there's a phase reversal between those vectors, and cancellation occurs again, just like it did on centerline. And let's start moving back to centerline. And the same process occurs to the left of centerline. Recall that 150 Hz predominates on the right of centerline and 90 Hz predominates on the left. We will now see how the audio phase relationships of the 90 and 150 Hz combines with the lobe phases produced by the antenna array to allow for this result. This assumes CSB and SBO are properly phased to each other. And here we see the relative RF lobe phases in magenta again. These RF lobe phase relationships affect transmitter audio phase relationships. So here we can see the 90 and 150 Hz audio phase signs remain unchanged in the positive lobes. However, audio phase is reversed in the oppositely phased lobe. Basically, all that's happened here is the SBO lobe left of centerline has reversed its audio phases. CSB then combines or space modulates with SBO, shown here by placing the CSB audio below each SBO audio. Now we just add them. Left of centerline, 90 Hz will vectorially add together with 150 Hz canceling. And right of centerline, 90 Hz vectorially cancels and 150 Hz add. An important fact of RF pattern development is the unavoidable creation of additional lobes. Between these lobes are nulls where the signal drops. Different techniques are used in the distribution network to develop the main lobe to be broad, thereby reducing the signal strength of these side lobes. However, this may not be practical due to adjacent local reflections such as buildings or taxiing aircraft. So to overcome these problems, the coarse signal must be narrowed, and a second RF pattern is radiated to mask these side lobes. An additional transmitter is used to develop this pattern at approximately 10 dB down from the coarse. Together they are known as the coarse and clearance, with each containing its own CSB and SBO signals. In 14 and 20 element arrays, these clearances are radiated from the inner 5 pair, known as a 1410 or 2010 array. So this concludes the Localizer RF pattern development lesson. In the next lesson, we'll discuss glide slope RF pattern development.